Hi, and welcome to Basilisk 2.0, the next generation of our spacecraft simulation software. This video is going to talk about this web page that you've just read, about how to translate scripts from Basilisk 1 to work with Basilisk 2. The key feature that Basilisk 2 provides is a brand new messaging system. Whereas before in Basilisk 1, there was a single message bulletin board, essentially, where modules had to request memory, got an ID, write to and from, and there's a lot of code involved. Now with the new messaging system, there's a direct peer-to-peer connections between the message objects. We no longer have a bulletin board, we have message objects which contain the data and the payload, as we call it, and they also have all the header information which knows, has this message been connected, when was it written? Has it ever been written? All those things we had before in Basilisk 1 is now still available in Basilisk 2. So the purpose of this web page was to really explain how to translate. And I'm making this video just to show you quickly some highlights of this web page and also go through an example. I think it's helpful to see what a Basilisk 1 script looked like and what I had to do to make it work in Basilisk 2. It's fairly mechanical. Typically, no logic changes have to happen for the most part. And all the features in Basilisk 1 still exist in Basilisk 2. They're just created and accessed differently, as you will see, often in a much easier, simpler way. The key feature we can take advantage of in Basilisk 2, though, is strong type checking. That means even in this layer of discussion about Basilisk, where we're only really talking about the Python layer, how do we create Basilisk Python simulations, is that even in Python, there's strong type checking. If you connect one message output to another's object's message input, and it's the wrong type, you're putting an attitude sensor and connecting it to a spacecraft position message, it's going to complain in Python and tell you, no, this is no good, which will make debugging so much easier. So let's go ahead and get started. First thing we can talk about is message names here. We used to have names because with this messaging board we had, everything had a name and had with a name and ID. All of that is gone now. There's no longer message names. There's no longer message IDs. There's just message object variables. So if we had a message name before called, for example, state out message name, and there would be typically in the module a state out message ID, those are gone, and you just have a single message object declaration called state out message. We kept the names very similar to before, so that way it's easy to identify, hey, that used to be the state out message name, now it's just a state out message. That's the output message, and I have to connect it to an input message. You can also still see the coding guidelines and how to name these things and go from there. Moving forward, importing just highlights, you see all the text here. Some things have moved. Basically, we used this opportunity to re-architect where things are. We had Basilisk architectural stuff somewhat stored inside simulation, which wasn't really the right place. So we moved some of those things outside. But the other thing, of course, is too, we used to have these SWIG files that had all the flight software message, another one that had all the interface, or another one that had all the simulation messages. This is all gone and simplified. Now we just have messaging. And so anytime you do anything messaging related, we're just going to import this one line from architecture, import messaging. So anyway, that's some highlights. Input, output names. Let's go through this one quickly too, just some highlights. We have some coding guidelines that we're using lower camel case for the names, and they're supposed to end with MSG, it's out MSG or in MSG. And some of the older modules didn't actually always abide by that. So we took this opportunity to kind of make this all much more consistent. That means some of the output message names have changed. Like for example, in attitude tracking error, there was one called output data message name. That was the old name thing. Of course, we don't have names anymore, but I've renamed that output message now attitude guidance out message. A little more descriptive of what it actually does. And it's now abides by our coding guidelines. So if something was simply correctly named, as before, we talked here, state out message name, then it's just going to be state out message, and I'm not listing it in this table. This table shows all the modules that had one or multiple names that were not compliant, and I wanted to show in one convenient place what I updated those names to. So if you're upgrading some module and you had Celestial 2-point, and you were connecting, somehow interacting, recording this message, you know, now it's not called output data, but act ref out, and so forth. If the module itself changed there was a few modules that used underscore, which also is against our naming conventions. I've renamed those to lower camel case, and you will see it on the first column. So anyway, so this is a convenient table that you can use to see if the module name changed, or within the module are one or more of the messages changed. And I try to highlight all of that stuff here. This will make your translation of scripts so much easier. Okay, now quickly going through. If we're working in Python, sometimes we have to create messages. You know, if you're doing flight software, we have to make a vehicle configuration message. If you're making a unit test on a module, you might want to create all the input messages just from Python and then feed your module specific stuff. So this is now actually much easier and simpler to do. As you can read here, first step is always import your messaging system. So it's the one shop for everything. It'll contain all the message definitions wrapped in C, wrapped in C++. It doesn't matter. It's all in there. Then to create it, this is the thing with the new message object. The message object contains a payload, which is your data, and it contains the header, which knows when it was written and all this other good stuff. So when you want to create a message object, there's really two steps as before. The first thing we always did is get a copy of the structure in Python, populate it with the right variables, and then there was this multi-step process to create a message and you know, request a message from the messaging system and doing all that. You will see that step is easier. So how do we make a copy of the payload structure? That's pretty easy. Those are all embedded within messaging. So if you have some message, this could be attitude guidance message, for example, it would be attitude guidance message payload, and then equal to some variable. So this variable is now a copy of the structure. You can do message data dot some variable name equal to 42, and you know, configure it. When it's time to write the message, you can do this in two steps. You make the message object. So that's done very similarly, messaging dot the particular message name, but without payload. If you just say particular message, you know, attitude guidance message, for example, brackets, this will create an instance of this message object. Actually, it makes a C++ instance of a message object. And that's going to be, I've just called it message here. Then if you want to write to it, there's a write method. So you do message.write, and you just give it the data. The time variable is actually optional. You can include it if you want. Many unit tests, we just do everything at the very first time. So its time is 0, so that's what it defaults to. But if you have to give a non-zero time, you can do that as well. Some tests start and stop, and then write the messages. So this way you give it the right time. If you want to give it a module ID, you can do that. By default, anything in Python that you write will have a module ID of 0. But if you need to override that for some reason, that's fine. C++ modules tend to have positive numbers, and Python modules that you can still create in Basilisk 2 will have negative ID numbers. But 0 just means this was a message created from the Python environment. This didn't impact really many scripts. If you want to do this message object creation, this is the message object creation and writing all in one line. This is actually quite common. You'll find this in a lot of scripts. You can create the object, write the data into it. And again, time is optional. It's set to 0. Anyway, so that's it. So now you can do a nice standalone message. If you need to connect something, I talk about it here in C++, you can actually redirect an object, a module, to not write to its own message copy, but to another one. In C++, you just have to equate them, which is easy. But in, yeah, and then we'll look at C wrapped messages below in a second. If you want to subscribe to it, so that's the key thing you typically always do. You have some module, you have some input message. Where does that message data come from? It comes from an output message. So we have this subscribe to command that you can then invoke onto any message. So whatever the module is, some input, subscribe to, and this could be a standalone message or a message with created in another module, anything like that. That will work just fine. Setting C-wrapped messages in Python. We don't have to do this much, really. The one place we have to do it is what's called gateway messages inside BSK Sim. If you're using BSK Sim, for example, you have different flight modes that all compute an attitude guidance solution. And then in the end, the same attitude guidance message is used in all the MRP feedback or attitude control systems and so forth. So several flight modes need to write to one message. And if you're a C module, like we have in flight mode, you have to write to a C wrapped standalone message. So that's why we showed this here. That's the purpose. Most of the scripts don't typically use this, but it's a different include. You have to go from architecture, include the C message, C interface wrapping in Python. You create the message like before. That's easy. This gives you your structure copy. You populate it. You would initialize it. That's important because that will connect the message to itself. If you just want to make a standalone message, or if you want to redirect it, there's an add author step that we have down here. This is where you can make one module not write to its own message, but say, look, make me an author somewhere else, and like a standalone. Then you have multiple things writing to one. So go look at the BSK sims if you're curious about that. For most people, this is not an issue. Reading a message, very simple. You can see here. If you start and stop the Basilisk simulation, at some point you want to get a copy of that message. It's really simplified now. You just say, hey, that object, whatever it is, like attitude tracking error, give me, dot guidance out message, dot read will just give you a copy of that structure. And then you can look at that structure, dot some variable, and see what that is. So again, much, much simpler. Connecting output to input messages. This is what we talked about earlier. This is the subscribe to command. So it doesn't matter if it was a C wrapped or a C++ wrapped. By default, everything is C++ objects in messaging because it's really transparent under the hood. So you can just go some message object, output, connect that to this input. And we do it by specifying the input dot subscribe to some output message. Again, very, very simple. Recording, what are some highlights here? The big change simply is before we had a Python-based system that would query the messaging architecture, the bulletin board, and go, okay, at this sampling period, go pull that message, make a copy in Python, and then we'd be able to pull it from the system and plot it. And in fact, when you asked for a three-dimensional vector, like an attitude set, it would prepend everything with the timestamp as well, all in one big array. That's what we used to have. Now with the new system, this is a little more elegant. We can create recorder objects. These are actual Basilisk modules. And you do that simply by, you have your module, either a C module or a C++ module, dot the output message that you want to record, dot recorder. This will automatically create a Basilisk object whose sole purpose is to run at a certain update period and just grab that message, copy, and record it. And it puts it in a standard vector. At the end, you can then, there's no pulling of data anymore because everything will be contained in this one variable that you can access. So it's much, much simpler. And because it is a Basilisk object at rec recorder, you have to actually add it to a task to be evaluated. And that's good. If you do it just by calling recorder with empty brackets, by default, it's going to update this module and pull that message at the rate of the task that is it running. So if you have a 10 Hertz task, you add this recorder, it's going to record at 10 Hertz. If you have a 10 Hertz task and you're going, hey, I'm adding this recorder, but really I only need it at 1 Hertz. You can do that here when you set up the recorder by giving it a sampling time in nanoseconds and just say, look, every second, record this every second. And then it will wait 10 time steps, 10 updates, and every 10th update, it'll pull the data and stash it. So it's nice for downsampling the data so you don't end up with these massive data files when you don't need them. There's a nice convenience function I want to highlight. You can compute this sampling time anytime, anywhere you wish, but with this sampling ratio method, you give it the total simulation time, you give it the time step. I'm running for 60 seconds and simulating at 10 Hertz, 0.1 seconds. And I wish to have 20 data points. It just computes with proper rounding, something that'll give you the closest to 20 data points that still include the endpoints. And yeah, so that will record it. Anyway, so these are kind of some highlights. If you start recording at a certain interval, you stop, you execute your simulation for 60 seconds, and then you go, okay, now I want to record something else, but I have to record this one at 5 Hertz, not 1 Hertz. You can change the sampling interval and then resume the simulation, and it'll start recording at that period. So this, as before, we had the capability, but it took much more code to do it. Now it is a very, very simple way to do it. The other thing to remember is I mentioned earlier that when you record the data, this recorder object, this Basilisk module, will contain a vector of all the message content, and it actually creates a time array separately. So when you get the data and say data something variable name, sigma bn or something that you want to record, pull out of that message, it's going to give you the 3 by n array of attitude measurements, those 3-dimensional attitude measurements. Before we had the time axis prepended, so that's no longer the case. The time is now separated out. And to pull the times, you would just do, your recorder object dot times would give you a 1-dimensional, n-dimensional, so a 1 by n basically, no, n by 1, I should say, array of timestamps. This was recorded at this nanosecond, this nanosecond, this nanosecond, as you had before, nanoseconds. But that comes in. So this might mean in your script, you might have to update your plotting routines, where before we often went from, we assumed the 0th element was time, and then 1, 2, 3 was the data sets. Now the data is just going to be in the variable, and 0, 1, 2, and time is pulled out separately. So when you run, another modification you will find is here, Initialize Simulation and Discover. This had to do with if you ran multiple processes, because by default, the processes didn't see each other's messaging, and you had to add all this code to connect these messaging systems. So, and then when you had to initialize, you also had to cross-connect all those messaging systems. With the new messaging system being peer-to-peer, you have one object here and one object in this process. You can just directly connect them, and you don't have to do anything else. So that's multi-process simulations are vastly simpler. And so there's no longer a need for Initialize Simulation and Discover, and then separately Initialize Simulation. So it's just now Initialize Simulation, simplified it. Other things, you will find a few macros defined that were in some other places that have not gone, defined in messaging.i. So like max effector number that was embedded actually in some of these flight software message interface files that we had. So that's now all put into messaging, and you can find them there. If you're not sure, go look at the sample scripts that run this stuff, scenarios or unit tests. You often find, great, that's what they're doing. And then you can quickly update it. So that's a quick rundown. What I'm going to do next is I'm going to actually share the screen that should show you an example. Yep, it worked. I'm showing here the scenario attitude feedback reaction wheel. It's complex enough that it doesn't, it has some interesting features, but it's not going to take too long to talk through. But also I'm showing you a git compare, so you can see on the left-hand side what Basilisk 1 looked like, and on the right-hand side what Basilisk 2 looked like. And what did I have to do to actually, upgrade my script to work? Well, with the imports, as we said, some of these names had changed. Things that had an underscore in them, MRP feedback, simple nav, have now been renamed to be compliant with our naming convention. So now it's just called MRP feedback and simple nav. So in the imports, you might have to do minor adjustments. Let's see what else we do. Then here in this one, we have a bunch of plotting methods. As before, you can see when we're plotting, it assumed the data was in slot 1, 2, and 3 for a 3-dimensional array. Now it's going to be slots 0, 1, 2 because slot 0 no longer is a timestamp. Time is provided separately. So your plotting routines might need some minor tweaking, and that's what you're seeing in here. I'm just going to zoom through this plotting stuff. Okay, now the actual simulation, we set up a task same way, we set up a process the same way. I'm naming the spacecraft something different. That's just a personal choice. Here you can see, for example, before within reaction wheel factory balanced wheels, it's one of those definitions that we had that's actually moved to messaging. So you can just access those variables from there. Creating a reaction wheel with the factory, all the changes that were required to do this and the outputs and connect things, everything is under the hood. So really no changes there are needed for your Python script, which is really nice. Then we create a variety of effectors. This one was missing a model tag, so I added it. But on the left side, you see there was an input command message called input commands. That was a horrible message name, and message names are gone. So that line is just deleted. In this script, you will find I moved all the subscriptions kind of to the end of the setup process. You could do it in line as you're creating modules, but just be aware you cannot subscribe one module module to another message if that other message doesn't exist yet. So here I chose to just do all the subscriptions after I created all the modules, but you can also do them incrementally as long as you have the right order. The rest of the changes, let's see, simple nav that got renamed. That's an easy fix, right, to Basilisk 2. So that would take you just a second to do. The next one, we're setting up all these flight modules right now and get things going. Actually, I missed one. I didn't want to highlight. We talked about reaction wheels at the factories. The use of the factories really hasn't changed. The same is true for Graph Body Factory. Creating Earth, creating Sun, creating all these objects, engaging with Spice, all of that is actually, you can go look at the sample scripts, but there's minimal, if any, changes. The Spice returns are slightly different, but just the basic gravity body setup, all the changes needed, how to connect graph body data, have the right input messages, all of that's under the hood. So if you use these graph body factories, you'll be very happy with the upgrade to Basilisk 2 because essentially no changes, or in most cases, no changes are needed. Now we're doing all the flight software stuff. And here you can see before we had to specify output names for everything and input names for some stuff. And so here, all of those are simply gone because I'm going to make these connections at the, later on in the script in one place. So anything with output names, input names is gone. MRP underscore feedback, again, is MRP feedback. That's an easy fix. All of this is basically, you can see this line here, for example, on the left side, it's connecting this attitude configuration output data name that was an output message to this input message by setting the names equal. That's how we used to subscribe one message to another. In the new system, we just do it with a direct command, no more names, and all subscribing is below. So I'm just going to keep scrolling up. Here's some different stuff that has all to do with messaging. All the message names are just simply taken out, and you'll see a big section here in a second where we do it. Logging, before we had to say with this Python command, log this message, tell it what message, and giving it a sampling time. This sampling time was the minimum time required. If you're running at 10 Hertz, you can tell it, look, just I know you're running at 0.1 second update periods, but only recorded no sooner than 0.3 seconds, right? That's what you used to do with sampling time. The same behavior is really with these new recording objects. So I'm specifying the number of points. I want 100 points. I know the simulation time, I know my time steps. So this little helper function gives me a sampling time. That'll get me pretty close to 100 points in these plots. Then I'm setting up a recorder. So for this object, this output message dot recorder, and I don't want to record at the simulation period. I want to record at this sampling time update rate. So that's what I'm specifying, and I get these recorder objects, which, because they're Basilisk modules, I have to add them to a task, which I do. So yeah, it's similar lines of code, but it will be actually, the pulling becomes way simpler because there isn't a pulling anymore. But this is how we update logging. And there was reaction wheel stuff, and I'm doing something similar here. I'm recording the reaction wheels having a vector of output messages. So I'm accessing each output message, creating a logger, and then I'm adding that logger or recorder to this simulation task. Same process, just it works with vectors of messages too. Then we had to make some standalone. The simulation required the flight software needed a vehicle configuration so we can pull the inertia. Before, we would create just a template structure definition from flight software, and you have to remember what's this message in flight software, in sim, or an interface. You don't have to remember that anymore. All of the messages now are just simply in messaging. There's no longer a distinction between flight software and sim and interface, which is making your life easier. Otherwise, it's the same thing, but except for having flight software in the message name, it just says message now, because it's just a message, and then payload tells me to make this data structure. This is what makes the same thing as what we had before. That's a simple example. Next line, you can see we just simply populate the inertia. Here we're putting the actual inertia into the flight software message. And then to write, compare this. This was all the old stuff you had to remember, where to write this, how to do it. There was this function that would create a message and write to the message, and it's doing a lot of things under the hood. Now, all you have to do is tell the messaging system here to create a vehicle config message object. And then in one line, I'm telling it also to do .write vehicle out to content. You note here, I'm not providing time. So this one will have a timestamp of 0. And the module ID will be 0 because it's created in Python. This is an example where you see we just had to update with just a few lines how to make a standalone message. The rest I have to make also a reaction wheel configuration message for flight software. We had two different ways to do it. You can see here quickly. That old command that we had is updated under the hood. So if your code just use that, you don't have to change anything. I have here the extra line because I'm showing also how you can create it with the other method. They both have their benefits. And here too, I don't think we had to change anything on the outer Python layer. Inside of these message things are all, updated to work with Python too. Now we're setting up the orbits. That's all the same. We're not doing anything messaging related. Viz interface. Before, we still have to provide it SCSIM. We have to actually add it. This function and creates a Viz interface object or module, Basilisk module, and then adds it to the task list called sim task name. That's why it needs these two first arguments. But before, we also had to need to know sim process, we had to know graph bodies, we had to know spacecraft name. That's no longer needed. This is way simpler. All you need to provide it now is the spacecraft object. Or if you have multiple, it can be in brackets, a list of objects. That works. And then from that object, it pulls the model tag. That will be your name. You no longer have to provide it separately. Graph bodies, we don't have to provide it. The spacecraft plus object contains a graph body effector, which knows which gravitational bodies are acting on the spacecraft. So it can pull all that information automatically. This is hugely simpler. Instead of having to give it a number of reaction wheels, and here the code required names with a very particular syntax. Now it's much easier. We just give it this reaction wheel effector list, which can be one reaction wheel per spacecraft, or you can also give a list of them. If you have multiple spacecraft, you make it a list. If you have 3 spacecraft and only spacecraft 1 and 3 have reaction wheels, second one doesn't, then you have a reaction wheel effector, comma, none, comma, reaction wheel effector 3, whatever you called it, right? You have to give it the same array size as spacecraft object list if you make it multi-spacecraft. Go see the scenario formation flying examples. They do that. Now, finally, here's all the new text because we deleted all the message creation. Somewhere we have to connect these things. And this is done here. The key to remember is we no longer have implicit names. Before we created Spacecraft Plus, its output message had a certain name. Simple Nav, its input message had the same in spacecraft state something name. So that by default, you create a spacecraft, it automatically connected to Simple Nav. That was nice, but it's also confusing. It's implicit, it's hidden. And if you have multi-spacecraft, it's very confusing because you create multiple objects and all of a sudden things all connect back to the first object, unless you go in and override. So that was the old system. With the new system, it's only explicit connections. So that's why here, the Simple Nav object, its input message has to be subscribed to the spacecraft output message that you see here. So this is where we make all those connections. Then attitude error, that input message connects to the Simple Nav, and you just go through the list. This is where we're making all these connections that we needed. Now we have all the messages complete. Next step, instead of doing a simulation and discover, we just do initialize simulation. As we said, we no longer have to do that discover step. And here before, we had to pull the data now from Python and tell it how long. If you got this wrong, it wouldn't pull the full. If you just set it to pull sigma, it would just pull the first value versus pulling 3, right? And you had to get all these numbers right. None of that is needed anymore. Now you just say, look, from that recorder object, dot whatever the variable name is of that message, motor torque in this case, dot motor torque, and this will give you now a copy, an NumPy array, of those motor torque vectors. This would be a n by 3 in this case. Same thing with sigma br. I'm just making local copies so it's easier. So these lines would get replaced with this, and then I can keep my same plotting stuff. That's why I'm doing that there. Same thing with wheels. And instead of pulling out the 0th element on the left side, this is how we got time before. Now we just have one of the recorder objects dot times, because in this example, every one of the recorder objects recorded at the same sampling period. They all have the exact same timestamps. So I can just pull one of them and use it for all of them. Yeah, that's it. And then the rest of it is these plotting routines, go pull these functions. We already updated them, and that was it. So you can see it takes just a little bit of work to go through, but for every step we did before, there's actually a cleaner, easier way to do it now with Basilisk 2. So I hope you enjoy using that. And All these scripts have been updated, so you can always compare old to new. If you want to look at one and going, how did they make this transition? You can go look at these scripts. Okay, thanks.